The James Webb Space Telescope achieved what many astronomers had spent entire careers hoping to witness. On a December morning in 2022, as scientists reviewed data from Webb's deep field observations, they found themselves staring at light that had traveled through space for more than 13 billion rupees. This light originated from a galaxy that existed when the universe was barely 300 million years old. A cosmic infant compared to its current age of 13.8 billion years. The discovery represented not merely a new record for the most distant galaxy ever observed, but a fundamental glimpse into an era that previous telescopes could only theorize about. This ancient galaxy, designated JGSC 1420, existed during the epoch when the first stars were igniting across the cosmos, when hydrogen and helium from the Big Bang were being forged into heavier elements, and when the universe was emerging from its dark ages. What Webb revealed about this galaxy and others from the same primordial era has challenged assumptions about how quickly galaxies could form after the Big Bang, how massive they could become so early, and what physical processes govern the infant universe. The search for the earliest galaxies has driven astronomical research for decades. Understanding galaxy formation is central to understanding cosmic evolution itself. Galaxies are not merely collections of stars scattered through space, but fundamental structures that organize matter, enable star formation, synthesize chemical elements, and create the conditions for planets and potentially life to emerge. Tracing galaxies back to their origins reveals how the universe transitioned from the smooth, nearly uniform state that existed shortly after the Big Bang to the richly structured cosmos we observe today, filled with galaxies of diverse sizes, shapes, and compositions. Before Webb, the most distant confirmed galaxies existed at redshifts around 11, corresponding to times when the universe was approximately 400 million years old. These galaxies had been painstakingly discovered using the Hubble Space Telescope combined with massive ground-based telescopes, requiring hundreds of hours of observation time and sophisticated analysis to distinguish genuine, distant galaxies from foreground objects that might mimic their appearance. Each new distance record pushed back the frontier of observable time by small increments, gradually extending our view toward the cosmic dawn. Webb was designed specifically to shatter these distance barriers. Its 6.5-meter primary mirror, composed of 18 gold-coated beryllium segments, collects far more light than Hubble's 2.4-meter mirror. More importantly, Webb observes primarily in infrared wavelengths rather than visible light. This infrared capability is crucial for detecting the most distant galaxies because of a phenomenon called osmological redshift. As light travels through expanding space, its wavelength stretches along with the expansion. Light that was emitted as ultraviolet or visible light from a galaxy in the early universe arrives at our telescopes shifted to infrared wavelengths after traveling billions of years. Through expanding space, the amount of redshift directly correlates with distance and look-back time, with higher redshifts corresponding to greater distances and earlier epochs. Galaxies at the edge of the observable universe have such extreme redshifts that their light shifts entirely out of visible wavelengths into the infrared, making them invisible to optical telescopes but perfect targets for Webb's infrared eyes. The telescope's instruments were specifically calibrated to detect light from galaxies with redshifts between 10 and 20, corresponding to the universe's first billion years. This era, known as the Epoch of Reionization, witnessed the first galaxies forming and their ultraviolet radiation gradually ionizing the neutral hydrogen that filled intergalactic space. When Webb's data from the JADES program began arriving, the science team implemented systematic searches for high redshift galaxies. JADES stands for JWST Advanced Deep Extragalactic Survey, a collaboration involving more than 80 astronomers from institutions worldwide. Allocated hundreds of hours of Webb observing time to study galaxy formation across cosmic history. The survey targeted small patches of sky that had been previously observed by Hubble during its deep field campaigns, particularly the region around the Hubble Ultra Deep Field and the Goods fields that Hubble had imaged repeatedly over years. Webb's observations went far deeper than Hubble's, detecting fainter objects and extending to longer infrared wavelengths. The strategy involved imaging each field through multiple filters that isolate different wavelength ranges, then using photometric techniques to estimate each detected galaxy's redshift based on how its brightness varies across different filters. High redshift galaxies show characteristic patterns where they appear bright at longer wavelengths, but disappear at shorter wavelengths. A signature called the Lyman break caused by absorption of ultraviolet light by neutral hydrogen. In Andron the galaxy that would become known as Jade's GSC-14 appeared as an unremarkable red dot in the initial images, easily overlooked among thousands of other faint sources. However, automated analysis flagged it as a potential extremely high redshift candidate based on its colors. Follow-up spectroscopy using Webb's near-infrared spectrograph confirmed what the photometry suggested. This galaxy existed at a redshift of 14.32, corresponding to a time just 290 million years after the Big Bang. Spectroscopy provides definitive redshift measurements by detecting specific spectral features, particularly the Lyman alpha emission line produced by hydrogen gas. In distant galaxies, this line shifts from its rest wavelength of 121.6 nanometers in the ultraviolet to infrared wavelengths proportional to the redshift. For Jade's GSC-14, the Lyman alpha line appeared at 1.86 micrometers, shifted by a factor of more than 15. Additional spectral features including other hydrogen lines and oxygen emission confirmed the redshift measurement beyond doubt. The discovery was simultaneously thrilling and perplexing. The galaxy itself presented properties that theories of early galaxy formation had not predicted. Cosmic time and distance. Measuring distances to galaxies billions of light years away requires understanding cosmology's relationship between distance, time, and redshift. The universe began approximately 13.8 billion years ago in the event we call the Big Bang, though this term is somewhat misleading because it suggests an explosion occurring at a specific location in pre-existing space. More accurately, the Big Bang represents the beginning of space and time themselves, with the universe expanding from an initially extremely hot, dense state. In the early moments, the universe contained no atoms, no stars, no structures of any kind. Only a soup of fundamental particles and radiation in thermal equilibrium at temperatures exceeding billions of degrees. As expansion continued, the universe cooled, allowing protons and neutrons to combine into atomic nuclei, and eventually, about 380,000 years after the Big Bang, cooling enough for electrons to combine with nuclei to form neutral atoms. This moment, called recombination, made the universe transparent to light for the first time. Before recombination, photons could not travel far without scattering off free electrons, keeping the universe opaque like the interior of a dense fog. After recombination, photons could stream freely through space, creating the cosmic microwave background radiation that we still detect today. Now cooled by expansion to microwave wavelengths and a temperature of 2.7 Kelvin. After recombination came the cosmic dark ages, a period lasting several hundred million years when the universe contained neutral hydrogen and helium but no luminous objects. Stars could not form immediately because the gas needed to collapse under gravity into dense enough clumps, and this required time. Small density fluctuations imprinted during the universe's first moments gradually grew through gravitational attraction, with denser regions pulling in surrounding matter and becoming denser still. Eventually, regions reached sufficient density that gravity overcame gas pressure, causing collapse into the first stars. These first stars, called population 3 stars, were likely very massive and formed from gas containing only hydrogen and helium without heavier elements. Modern stars form from gas enriched with elements like carbon, nitrogen, oxygen, and iron produced in previous generations of stars. And these elements affect how gas cools and fragments during star formation. The first stars formed from pristine primordial gas that cooled less efficiently, favoring the formation of fewer, more massive stars rather than the diverse stellar populations seen in modern galaxies. The first stars ignited roughly 100 to 200 million years after the Big Bang based on current models. Though the exact timing remains uncertain, These stars emitted intense ultraviolet radiation that began ionizing the surrounding neutral hydrogen, creating bubbles of ionized gas that expanded and eventually merged as more stars formed. This process, the epoch of reionization, gradually transformed the universe from neutral to ionized over several 100 million years. The first galaxies formed during this epoch as stars clustered together in gravitationally bound systems. These early galaxies were small compared to modern galaxies, containing millions or tens of millions of solar masses of stars rather than hundreds of billions like the Milky Way. Current theories suggest that galaxies grow through two main processes: smooth accretion of gas that falls into the galaxy's gravitational potential and cools to form new stars, and mergers where smaller galaxies collide and combine to form larger systems. Over cosmic time, repeated mergers and ongoing gas accretion built the massive galaxies we observe in the nearby universe today. Measuring distances to these early galaxies relies on understanding how redshift relates to cosmic expansion. The redshift parameter Z is defined as the fractional change in wavelength. Z equals the observed wavelength minus the emitted wavelength divided by the emitted wavelength. For example, light emitted at 500 nanometers that is observed at 1000 nanometers has a redshift of 1. In an expanding universe, redshift directly relates to the cosmic scale factor, which describes how distances between galaxies have grown with time. A galaxy at redshift Z emitted its light when the universe was smaller by a factor of 1 plus Z. For JHGSC 142 at redshift 14.32, the universe was 15.32 times smaller when the light was emitted than it is today. Converting redshift to look-back time and distance requires a cosmological model that describes the universe's expansion history. The standard model, called lambda CDM, includes ordinary matter, dark energy, and radiation, with specific parameters determined from observations of the cosmic microwave background, supernova distances, galaxy clustering, and other cosmological probes. Using lambda CDM cosmology with current best fit parameters, a redshift of 14.32 corresponds to a look-back time of 13.51 billion years, meaning we observed JHGSC 140 as it appeared just 290 million years after the Big Bang. The distance to this galaxy is more subtle to define because space itself expands. The co-moving distance, which accounts for expansion and represents the distance to the galaxy in today's coordinates, is approximately 33.5 billion light-years, even though the light traveled for only 13.51 billion years. This apparent paradox resolves when recognizing that the galaxy was much closer when it emitted the light we now detect, but space has expanded during the light's journey, carrying the galaxy to its current great distance. Another relevant distance measure is the light travel distance of 13.51 billion light-years, representing how long the light traveled and how far back in time we are observing. For practical purposes, astronomers typically discuss high redshift galaxies in terms of their age when observed, saying that JHGSC 140 is seen when the universe was 290 million years old. Avoiding confusion about distance definitions, the significance of discovering galaxies at such early times is that we directly observe an era that was previously accessible only through theoretical inference. Computer simulations of structure formation in the early universe predict when and how the first galaxies should form based on the physics of gravitational collapse, gas cooling, star formation, and feedback processes where stellar radiation and supernovae inject energy into surrounding gas. These simulations begin with initial conditions matching the cosmic microwave background's observed properties and evolve forward following physical laws implemented in computational codes. Predictions from simulations can be compared to observations, testing whether our understanding of the relevant physics is correct. Before Webb, observations had constrained galaxy properties down to redshifts around 10 to 11, corresponding to roughly 400 to 500 million years after the Big Bang. This data generally agreed with simulation predictions, showing galaxies with masses, sizes, and star formation rates consistent with models. Webb's ability to observe back to 290 million years, and potentially even earlier, provides more stringent tests in an epoch where theoretical predictions are less certain and depend more sensitively on assumptions about the first star formation and feedback processes. The properties of ancient light JHGSC 140 is not merely distant but possesses physical properties that have prompted intense scientific discussion. Initial measurements indicated a galaxy surprisingly large and luminous for such an early cosmic epoch. The galaxy's brightness and Webb's infrared images suggests it contains a substantial stellar population, with estimates indicating a stellar mass around several 100 million times the mass of our Sun. For comparison, the Milky Way contains approximately 60 billion solar masses of stars, so this ancient galaxy is modest by modern standards. However, it existed when the universe was only 290 million years old, leaving very little time for stars to form and accumulate into such a massive system. Simple calculations illustrate the challenge. If star formation began 100 million years after the Big Bang, the galaxy would have had only 190 million years to build its stellar mass. Achieving several 100 million solar masses in this time requires sustained star formation rates that push the limits of what theoretical models consider plausible for such small systems in the early universe. The galaxy's size adds another puzzle. Measurements of its spatial extent from Webb's high-resolution imaging indicate a physical diameter of approximately 1,600 light-years. Compact compared to typical modern galaxies but substantial for such an early object. The combination of mass and size determines the galaxy's stellar density, and JDSGSC 140 shows a relatively high density consistent with predictions that early galaxies should be compact, forming stars efficiently in dense environments before later interactions and gas accretion cause them to expand. However, the fact that such a compact, massive galaxy could assemble so quickly challenges understanding of how rapidly dark matter halos could grow in the early universe and how efficiently gas could cool and form stars within them. Dark matter halos provide the gravitational scaffolding within which galaxies form, and simulations predict that more massive halos took longer to assemble from smaller progenitors through hierarchical merging. The existence of a relatively massive galaxy at redshift 14 suggests either that dark matter halos grew faster than standard models predict, or that star formation efficiency in early galaxies was higher than assumed. Spectroscopic observations revealed additional details about the galaxy's physical conditions. Emission lines in the spectrum indicate that the galaxy contains not only hydrogen and helium but also heavier elements including oxygen and carbon. These elements, collectively called metals in astronomical terminology regardless of their chemical properties, were not present in the primordial universe but must be produced through nuclear fusion in stars. Massive stars fuse hydrogen into helium, then helium into carbon and oxygen. And the most massive stars continue fusing elements up to iron. When these massive stars explode as supernovae, they disperse these newly formed elements into surrounding gas, enriching it and enabling subsequent generations of stars to form from chemically enriched material. The presence of oxygen and carbon in JHGSC 140 confirms that at least one generation of stars had already formed, lived their lives, and exploded before the stars we currently observe were born. This requires pushing the first star formation back even earlier, likely to within 100 to 150 million years after the Big Bang, giving enough time for the first stars to complete their evolution. The oxygen abundance in JHGSC 140, estimated from the strength of oxygen emission lines relative to hydrogen lines, is approximately 1/10 of the Sun's oxygen abundance. This is remarkably high for such an early galaxy. The Sun formed 4.6 billion years ago from gas already enriched by many previous generations of stars, giving it relatively high metal content. Finding a galaxy at redshift 14 with 1/10 solar metallicity suggests that chemical enrichment proceeded rapidly in the early universe, more rapidly than some models predicted. Possible explanations include very efficient star formation that quickly converted gas into stars, with supernovae from short-lived massive stars rapidly enriching the remaining gas. Alternatively, the first generation of population 3 stars might have been more effective at producing metals than standard models assume, either because they were more massive on average or because supernovae dispersed metals more efficiently. Another possibility is that the galaxy experienced very early mergers with other small galaxies that had already undergone chemical enrichment, pooling their enriched gas to create the system we now observe. The galaxy's star formation rate, estimated from its ultraviolet luminosity, indicates it is actively forming stars at a rate of approximately 3 to 5 solar masses per year. For comparison, the Milky Way currently forms roughly 2 solar masses of stars annually, so this ancient galaxy is similarly active despite being much smaller. This high specific star formation rate, meaning the star formation rate divided by existing stellar mass, characterizes a galaxy rapidly building its stellar population rather than a mature system forming stars slowly. The sustainability of such star formation rates depends on the galaxy's gas supply. Stars form from dense molecular gas, and once a galaxy's gas is consumed, star formation must cease unless fresh gas is accreted from the surrounding intergalactic medium and the early universe. Galaxies were embedded in relatively dense environments with abundant gas available for accretion, supporting high sustained star formation rates. However, stellar feedback processes including radiation pressure from young massive stars and shock waves from supernovae can heat and expel gas from galaxies, temporarily or permanently suppressing star formation. Balancing these processes determines how efficiently early galaxies could convert their available gas into stars. The ultraviolet light that Webb detects from JADE's GSC 140, now shifted to infrared wavelengths, was originally emitted by hot, young stars with surface temperatures exceeding 10,000 Kelvin. These stars, more massive than the Sun, live only millions to tens of millions of years before exhausting their nuclear fuel and exploding. The ultraviolet light we observe therefore traces very recent star formation, showing that the galaxy was actively producing stars at the moment we observe it, 290 million years after the Big Bang. The galaxy's ultraviolet brightness exceeds what was expected for galaxies at this epoch based on extrapolations from low redshift observations. Before Webb, astronomers had constructed models predicting the number of galaxies at different brightnesses and redshifts, based on observations extending to redshift 10 or 11 and theoretical modeling of earlier epochs. These models generally predicted that at redshift 14, galaxies should be very faint and rare because insufficient time had elapsed for large stellar populations to accumulate. JADE's GSC 140 and several other high redshift galaxies Webb has discovered are brighter than these predictions suggested, indicating that galaxy formation proceeded more efficiently or began earlier than standard models assumed. Challenging theoretical predictions, the discovery of JADE's GSC 140 and other massive early galaxies has sparked debate about whether standard cosmological models require revision. The lambda-CDM model has been extraordinarily successful at explaining a wide range of cosmological observations, including the cosmic microwave background's detailed properties, the large-scale distribution of galaxies, the abundances of light elements produced during Big Bang nucleosynthesis, and the acceleration of cosmic expansion revealed by distant supernovae. However, no model is beyond challenge, and observations that disagree with predictions must be carefully examined to determine whether they indicate problems with the model or merely reflect uncertain assumptions about specific physical processes. In the case of early massive galaxies, the question is whether their existence contradicts fundamental aspects of lambda-CDM cosmology, particularly the growth rate of density fluctuations that seed galaxy formation, or whether they can be accommodated within the model by adjusting assumptions about star formation, efficiency, and other astrophysical processes. Dark matter density fluctuations in the early universe grew through gravitational instability following patterns determined by the fluctuation's initial amplitude, the universe's expansion rate, and the properties of dark matter itself. In lambda-CDM, these fluctuations had very small amplitude initially, typically characterized as variations of order 1 part in 100,000 in density. Gravitational instability amplified these fluctuations over time, with denser regions growing denser as they attracted surrounding matter. The growth rate depended on the balance between gravity pulling matter together and cosmic expansion pulling it apart. In the early matter-dominated universe, gravity won decisively. allowing fluctuations to grow rapidly. By redshift 14, fluctuations had amplified by factors of hundreds, creating a population of dark matter halos ranging from millions to hundreds of millions of solar masses. Standard simulations predict the abundance of halos at different masses and redshifts based on lambda CDM parameters measured from cosmic microwave background observations. These predictions can be compared to observations of high redshift galaxies, assuming some relationship between halo mass and the stellar mass of galaxies that form within them. The stellar mass to halo mass relationship is not predicted from first principles but must be modeled based on understanding of gas cooling, star formation, and feedback processes. In general, more massive halos can host more massive galaxies, but the relationship is not one-to-one because the efficiency of converting gas into stars varies with halo mass and cosmic epoch. Several factors affect efficiency and low-mass halos. Supernova feedback can expel gas more easily because the halo's gravitational binding energy is smaller, reducing star formation efficiency. In very massive halos, gas heating by various processes can prevent gas from cooling and forming stars, again reducing efficiency. Intermediate mass halos, roughly corresponding to the Milky Way's mass range, achieve peak efficiency where substantial stellar masses accumulate. For high redshift galaxies, additional complications include the potential role of population 3 stars, which might form with different efficiencies and produce different feedback effects than later stellar generations. Uncertainty in these processes means that the predicted stellar masses for galaxies at redshift 14 have significant error bars. Comparing Webb's observations to predictions reveals tension but not clear contradiction. Some models predict that galaxies as massive as JADE's GSC 140 should be extremely rare at redshift 14. Potentially with number densities so low that finding even one in Webb's survey volume would be unlikely. Other models with slightly different assumptions predict higher abundances where discovering several such galaxies isn't surprising. The key question is whether the observed abundance and properties of high redshift galaxies can be explained within lambda CDM cosmology by reasonable adjustments to astrophysical assumptions, or whether the discrepancies are so large that fundamental cosmological parameters require revision. Initial analyses suggest that adjustments to astrophysical models can likely accommodate the observations. For example, if star formation efficiency in the first galaxies was higher than standard assumptions, or if population 3 stars formed more efficiently and enriched gas more rapidly, then more massive galaxies could exist at earlier times. These possibilities remain within the framework of lambda CDM cosmology, which specifies the growth of dark matter structure but not the details of star formation within that structure. Alternative explanations invoke modifications to cosmology itself. Some researchers have suggested that if dark matter properties differed from standard assumptions, perhaps interacting with ordinary matter or radiation more strongly, or if dark energy's properties evolved differently with cosmic epoch, then structure formation timelines might shift, allowing earlier galaxy formation. More exotic proposals suggest that the initial density fluctuations might have been larger than cosmic microwave background observations indicate, perhaps containing features at small scales not directly constrained by microwave background data. Each of these alternatives faces challenges because they must not only explain the new high redshift galaxy observations but also remain consistent with all other cosmological data, including the cosmic microwave background's detailed power spectrum, the distribution of galaxies at lower redshifts, element abundances from Big Bang nucleosynthesis, and gravitational lensing measurements that constrain dark matter distributions. Modifying lambda CDM to fix one problem while avoiding conflicts with other observations is difficult, which is why most researchers favor exploring astrophysical solutions within the standard cosmology Cal framework before invoking fundamental cosmological changes, the scientific process of resolving this tension will unfold over years through multiple avenues. Additional Webb observations are expanding the census of high redshift galaxies, providing better statistics on their abundance, mass distribution, and properties. Larger samples constrain models more tightly because they reduce statistical uncertainty about whether observed galaxies represent rare outliers or typical members of a populous class. Improved theoretical models incorporating updated physics of star formation, feedback, and chemical enrichment will refine predictions for comparison with data. Simulations with higher resolution can resolve smaller structures and capture processes operating at finer scales, potentially revealing physical mechanisms that coarse simulations miss. Observations at different wavelengths will complement Webb's infrared data, with radio observations detecting emission from ionized gas and cold molecular clouds, and future X-ray missions potentially detecting hot gas and black holes in early galaxies. This multi-wavelength approach builds comprehensive pictures of early galaxies that no single facility can provide alone. The first stars and chemical enrichment understanding JADE's GSC 140 requires understanding the first stars that preceded it. These population 3 stars formed from gas containing only hydrogen and helium, lacking the heavier elements that affect star formation in later cosmic epochs. The absence of metals significantly altered gas cooling processes. In modern star-forming regions, molecules like carbon monoxide and water vapor radiate away thermal energy efficiently, allowing gas clouds to cool to very low temperatures around 10 Kelvin. This cold gas fragments into many small clumps that collapse to form stars across a range of masses from less than 1 solar mass to tens of solar masses. Population 3 star formation occurred in gas that could cool only through molecular hydrogen, a much less efficient coolant that could lower temperatures only to about 200 to 300 Kelvin. At these higher temperatures, thermal pressure supported larger masses against gravitational collapse, favoring formation of very massive stars potentially ranging from tens to hundreds of solar masses, rather than the diverse stellar populations formed today. These massive first stars had short lives because nuclear fusion proceeds very rapidly in high-mass stars. A star 10 times the Sun's mass lives about 30 million years, while a 100 solar mass star might survive only 3 million years. During their brief lives, these stars fused hydrogen into helium in their cores, then fused helium into carbon and oxygen, and for the most massive stars, continued through successive burning stages producing neon, magnesium, silicon, and finally iron. The fusion process released tremendous energy that supported the star against gravitational collapse, but once the core consisted of iron, no further fusion could occur because fusing iron requires energy input rather than releasing energy. With fusion shut down, the core collapsed catastrophically, triggering a supernova explosion that blasted the star's outer layers into space at velocities of thousands of kilometers per second. This explosion dispersed the heavy elements synthesized during the star's life, mixing them into surrounding gas and enriching it with the first metals in the universe. The first supernovae were dramatic events that profoundly affected their surroundings. The explosion energy exceeded the gravitational binding energy of the small dark matter halos where population 3 stars formed, meaning the supernova blast wave could expel gas entirely from these halos, shutting down further star formation at least temporarily. The hot, metal-enriched gas expelled by supernovae mixed into the intergalactic medium, spreading metals across regions much larger than individual halos. Subsequent gas accretion onto nearby halos brought metal-enriched gas into regions where second-generation stars could form. These population 2 stars formed from gas with small but non-zero metal content, and the presence of metals altered cooling and fragmentation, allowing lower-mass stars to form in addition to massive ones. Multiple generations of star formation and supernova enrichment progressively increased metallicity, creating the chemical evolution observed in later galaxies including JADE's GSC 140. The timeline of these events depends on when the first stars formed and how quickly they evolved and exploded. Current models suggest population 3 star formation began roughly 100 to 200 million years after the Big Bang, though significant uncertainty remains. The formation timing depended on how quickly gas could accumulate in the first dark matter halos and cool sufficiently to collapse once formed. The most massive population 3 stars lived only a few million years before exploding, so chemical enrichment could begin within 200 million years or less after the Big Bang. By the time JHGSC 1420 is observed at 290 million years, several cycles of star formation and enrichment could have occurred, explaining the galaxy's substantial oxygen abundance. However, achieving 1/10 solar metallicity in such a short time requires highly efficient enrichment, suggesting either that star formation and supernova rates were very high, or that mixing and gas recycling processes operated very effectively to spread metals through the galaxy's gas reservoir. The presence of specific elements in JHGSC 140's spectrum provides clues about the types of stars that produced its chemical enrichment. Oxygen, detected through strong emission lines in the spectrum, is produced primarily in massive stars through helium burning. Carbon is also detected, produced through similar processes. The ratio of oxygen to carbon can constrain the mass distribution of stars that contributed to enrichment because stars of different masses produce these elements in different ratios. Preliminary analysis suggests that the carbon-to-oxygen ratio in JHGSC 140 resembles what would be produced by a population of massive stars, consistent with expectations if population 3 stars were predominantly high-mass objects. More detailed analysis comparing observed abundance patterns to predictions from stellar evolution models will refine understanding of what stellar populations contributed to the galaxy's chemical enrichment. Nitrogen is another element of interest because it forms through different processes than oxygen and carbon. Nitrogen can be produced in lower mass stars through the CNO cycle, where carbon, nitrogen, and oxygen catalyze hydrogen fusion. Detecting nitrogen in high redshift galaxies would indicate that lower mass stars had sufficient time to evolve, contribute to enrichment, and disperse their processed material. Current Webb spectra of JHGSC 140 have not clearly detected nitrogen, which may indicate either that it is below detection limits or that the enrichment primarily came from massive stars that use relatively little nitrogen. Future deeper spectroscopy may detect nitrogen lines and provide additional constraints on the enrichment history. Iron is yet another critical element because it forms primarily in core-collapse supernovae from massive stars and type Ia supernovae from white dwarf explosions. Type Ia supernovae occur when white dwarfs in binary systems accrete matter from companions and explode, processes that require timescales of hundreds of millions of years or longer. At redshift 14, type Ia supernovae may not yet have contributed significantly to enrichment, meaning iron abundance should be lower relative to oxygen compared to later cosmic epochs when type Ia supernovae have enriched galaxies. Measuring iron in JHGSC 140 would test this prediction. Though iron lines are typically fainter and harder to detect than oxygen lines in distant galaxies. The epoch of reionization JHGSC 140 existed during the epoch of reionization, a transformative period when the first luminous objects reionized the universe's hydrogen. After recombination at 380,000 years, hydrogen throughout the universe became neutral, consisting of protons and electrons bound together as atoms. This neutral hydrogen remained the dominant state for hundreds of millions of years during the cosmic dark ages. Neutral hydrogen absorbs ultraviolet light at wavelengths shorter than 121.6 nanometers. The Lyman alpha wavelength corresponding to the atomic transition between hydrogen's ground state and first excited state. This absorption made the universe opaque to ultraviolet light, preventing photons from traveling far through intergalactic space. When the first stars and galaxies formed, they emitted intense ultraviolet radiation with photons energetic enough to ionize hydrogen, splitting atoms into free protons and electrons. Each massive star produced vast numbers of ionizing photons, creating an expanding bubble of ionized hydrogen around it. As more stars formed in early galaxies, these ionized bubbles grew and eventually merged, progressively ionizing larger volumes. The reionization process was patchy and inhomogeneous because star formation occurred first in regions where dark matter halos formed earliest, typically in locally denser regions of the universe. These regions reionized first while lower density regions remained neutral longer. Cosmological simulations of reionization show a complex evolving pattern of ionized bubbles growing and merging over several hundred million years. The timeline of reionization is constrained by several observations. The cosmic microwave background's polarization, measured by satellites like WMAP and Planck, provides integrated constraints suggesting reionization occurred primarily between redshift 6 and 10, corresponding to roughly 500 million to 1 billion years after the Big Bang. Observations of distant quasars, supermassive black holes accreting gas and shining with immense luminosity, show absorption features indicating substantial neutral hydrogen remained in the intergalactic medium at redshift 6 and beyond. By redshift 5, quasar spectra indicate the intergalactic medium was largely ionized, completing reionization. JADSGSC140 at redshift 14.3 existed well before reionization completed, likely during the early stages when ionized bubbles were just beginning to grow. The galaxy itself contributed to reionization by producing ionizing photons that created an ionized region around it. The size of this ionized region depended on the galaxy's ionizing photon production rate and the density of surrounding neutral hydrogen. A typical early galaxy might ionize a bubble a few million light-years across, small compared to the hundreds of millions of light-years between distant galaxies but significant locally. The observation that we can detect Lyman alpha emission from JADE's GSC140 has interesting implications. Lyman alpha photons are absorbed by neutral hydrogen, so detecting them suggests the region around the galaxy was at least partially ionized, allowing Lyman alpha photons to escape and travel through space to reach Webb. However, even in an ionized bubble, Lyman alpha photons scatter off neutral hydrogen atoms at the bubble's edge and in residual neutral hydrogen within the bubble, affecting the line's observed properties including its shape and intensity. The cumulative effect of many early galaxies gradually reionized the entire universe. Theoretical models calculate whether observed galaxies produce enough ionizing photons to complete reionization by the observed redshift around 6. This calculation involves several factors: the number density of galaxies at different epochs, the ionizing photon production rate per galaxy determined by star formation rate and stellar population PR properties, the fraction of ionizing photons that escape galaxies rather than being absorbed by gas and dust within the galaxy, and the recombination rate at which ionized hydrogen captures free electrons and returns to neutral, requiring reionization. Balancing these factors determines how quickly reionization proceeds. Pre-Webb models suggested that galaxies observed by Hubble, primarily at redshift 6 to 10, could provide enough ionizing photons to complete reionization if their ionizing photon escape fractions were reasonably high, around 10 to 20%. Webb's discovery of numerous galaxies at redshifts beyond 10, including JADSGSC140, adds additional sources of ionizing photons that accelerate reionization, making it easier to achieve complete reionization by the observed epoch. However, uncertainties remain about escape fractions and whether early galaxies' ionizing photons could escape into the intergalactic medium. Ionizing photons are absorbed by neutral hydrogen within galaxies, and only photons that avoid absorption can contribute to reionizing the intergalactic medium. The escape fraction depends on the distribution of neutral hydrogen in and around galaxies, which in turn depends on star formation geometry, feedback processes that clear gas channels, and the clumpiness of the interstellar medium. Some observations of lower redshift galaxies analogous to early systems suggest escape fractions ranging from a few percent to over 50% depending on galaxy properties. High escape fractions occur in galaxies with intense star formation that creates hot bubbles and supernovae-driven winds that carve channels through which ionizing photons escape. JADSGSC140's compact size and high star formation rate suggest it might achieve relatively high escape fractions, making it an efficient contributor to reionization despite its small size. Measuring escape fractions directly in high redshift galaxies is challenging because it requires detecting the escaping ionizing photons, which are absorbed by any intervening neutral hydrogen in the intergalactic medium. At redshift 14, the intergalactic medium was largely neutral, absorbing ionizing photons before they could travel cosmological distances to reach our telescopes. Indirect methods estimate escape fractions by measuring the strength of emission lines produced by ionizing photons within galaxies and comparing to stellar population models that predict how many ionizing photons the stars produce. Discrepancies between observed and predicted line strengths constrain how many photons must have escaped. These methods applied to JADE's GSC 1420 suggest moderate escape fractions around 10 to 30%. Though significant uncertainty remains, future observations with improved sensitivity and spectral resolution will refine these estimates and determine whether early galaxies like JADE's GSC 140 provided ionizing photons needed to ionize the universe, or whether additional sources such as faint dwarf galaxies or exotic objects like primordial black holes contributed significantly. Supermassive black holes. An unexpected aspect of early galaxy discoveries involved supermassive black holes. Nearly every massive galaxy in the nearby universe hosts a supermassive black hole at its center, with masses ranging from millions to billions of solar masses. These black holes grow through accretion of gas and through mergers when galaxies collide, and their central black holes eventually coalesce. The relationship between black hole mass and the properties of their host galaxies, particularly the stellar velocity dispersion in the central bulge, suggests a deep connection between black hole growth and galaxy evolution. How supermassive black holes form and grow remains an active research area because forming billion solar mass black holes by redshift 6, when they are observed as luminous quasars, requires either very massive black hole seeds or extremely rapid growth rates that push theoretical limits. Webb has discovered several distant quasars powered by supermassive black holes at redshifts beyond 10, existing when the universe was less than 500 million years old. These black holes have masses exceeding 100 million solar masses, posing significant theoretical challenges. Black holes grow by accreting gas from their surroundings, with the accretion rate limited by the Eddington limit, the maximum rate at which a black hole can accrete before radiation pressure from the accreting material pushes away inflowing gas. Accreting at the Eddington limit, a 10 solar mass black hole takes roughly 700 million years to grow to 100 million solar masses through exponential growth. To achieve this mass by 500 million years after the Big Bang requires either that black hole seeds formed very early, within tens of millions of years after the Big Bang, and grew continuously at the Eddington limit, or that growth exceeded the Eddington limit through super-Eddington accretion, or that seeds were more massive than typically assumed. The nature of black hole seeds is debated. Stellar mass black holes form when massive stars exhaust nuclear fuel and collapse, creating black holes of approximately 10 to 100 solar masses. Starting from such seeds, reaching supermassive black hole scales by redshift 6 requires nearly continuous maximum rate accretion, which seems unlikely because accretion is typically episodic, with periods of rapid feeding interspersed with quiescent intervals when gas supplies are exhausted or feedback from the black hole temporarily halts infall. Alternative seeding mechanisms include direct collapse of massive gas clouds into black holes of thousands to tens of thousands of solar masses without forming stars first. This process requires specific conditions including suppression of star formation within collapsing clouds, possibly achieved if molecular hydrogen is destroyed by radiation from nearby sources, preventing gas from cooling to form stars and allowing collapse directly into a black hole. Another hypothesis suggests that dense stellar clusters in early galaxies could collapse through runaway stellar mergers, forming intermediate mass black holes of hundreds to thousands of solar masses that serve as seeds. JADE's GSC 140 itself shows tentative evidence for an active galactic nucleus, the signature of a central supermassive black hole accreting gas and emitting radiation. Specific emission lines in the galaxy's spectrum, particularly broad components of hydrogen lines indicating gas moving at high velocities, suggest accretion onto a black hole. The inferred black hole mass is roughly 1 million solar masses, smaller than the billion solar mass behemoths in distant quasars but still requiring explanation for how it formed and grew by redshift 14. A 1 million solar mass black hole likely originated from a seed of thousands of solar masses that grew over 100 to 200 million years, whether such seeds form from population 3 stellar remnants, direct collapse, or stellar cluster collapse remains uncertain. The observation that even relatively small galaxies like JADE's GSC-14 may host substantial black holes suggests that black hole formation was ubiquitous in the early universe. Not restricted to the most massive systems, the coevolution of black holes and galaxies is thought to involve feedback processes where energy from accreting black holes affects star formation in the host galaxy. As gas falls toward a supermassive black hole, it heats through compression and friction in an accretion disk surrounding the black hole, emitting intense radiation across the electromagnetic spectrum. This radiation heats surrounding gas and can drive powerful winds that blow gas out of the galaxy, temporarily or permanently suppressing star formation. This negative feedback may explain why the most massive galaxies in the nearby universe form stars inefficiently despite residing in massive dark matter halos with abundant gas supplies. The central black holes have grown sufficiently massive that their feedback energy prevents from cooling and forming stars. In early galaxies like JAD's GSC-1420, black holes were smaller and feedback effects weaker, allowing efficient star formation to proceed. Understanding the balance between black hole growth, star formation, and feedback at different cosmic epochs remains a key goal of galaxy evolution studies. Gravitational lensing and magnification. Some of the earliest galaxies Webb has discovered benefit from gravitational lensing, a phenomenon predicted by general relativity where mass bends spacetime and deflects light rays passing nearby. Massive galaxy clusters containing trillions of solar masses of matter, mostly dark matter, create substantial spacetime curvature that acts as a gravitational lens, magnifying and distorting the images of more distant background galaxies. In fortunate alignments, a distant galaxy lies directly behind a foreground cluster as seen from Earth, and the cluster's gravity magnifies the distant galaxy's light by factors of 10 to 100 or more, making intrinsically faint objects detectable and allowing detailed study of galaxies that would otherwise be too faint even for Webb. The magnification is not uniform across the lensed galaxy's image, and often the background galaxy appears stretched into arcs or split into multiple images depending on the precise alignment and mass distribution of the lensing cluster. Webb has observed several massive galaxy clusters known to be powerful lenses, searching for highly magnified high-redshift galaxies. These observations have discovered numerous candidates at redshifts exceeding 10, with some potential candidates at redshift 16 or beyond, corresponding to times just 200 to 250 million years after the Big Bang. Confirming these extreme redshifts requires spectroscopy, which is challenging even with Webb because the galaxies are intrinsically faint despite magnification. However, the magnification allows spatially resolving structures within distant galaxies that would be impossible to observe without lensing. In some cases, individual star-forming regions within high redshift galaxies can be distinguished, revealing clumps a few hundred light-years across where star formation concentrates. This spatial information provides insights into how early galaxies organize their star formation, whether in distributed regions throughout the galaxy or in concentrated nuclear starbursts. Gravitational lensing also enables measurements of the total mass of lensing clusters through modeling how much mass is required to produce the observed image distortions. Detailed lensing models incorporate multiple lensed background galaxies at different redshifts, each providing constraints on the cluster's mass distribution. The resulting models reveal that clusters contain far more mass than visible in stars and hot gas, confirming dark matter's presence and mapping its distribution. Some lensing analyses have detected discrepancies between predicted and observed lensing effects on small scales, potentially indicating substructure in dark matter halos or complexities in mass distribution not captured by smooth models. These discrepancies are important for understanding dark matter's nature and whether it interacts through forces beyond gravity. One particularly interesting lensed galaxy, designated MACS06 for 7JD, was originally discovered by Hubble but studied in detail by Webb with spectroscopic follow-up. This galaxy at redshift 10.3 shows spatial structure resolved by lensing into 3 distinct star-forming clumps, suggesting that the galaxy may be undergoing a merger of smaller subgalaxies. If confirmed, This would represent a merger occurring just 460 million years after the Big Bang, demonstrating that galaxy assembly through mergers began very early. The clumps show different colors in Webb's images, indicating different stellar populations or dust content, with one clump appearing redder suggesting either older stars or more dust. The ability to resolve such structure in a galaxy at redshift 10 showcases lensing's power and motivates continued observations of lensing clusters to find and study additional magnified early galaxies. Limitations of lensing studies include uncertainties in magnification factors, which depend on detailed lens models. Different modeling assumptions or mass distribution parameterizations can yield magnification estimates that differ by factors of 2 or more, affecting derived intrinsic luminosities and stellar masses of lensed galaxies. Additionally, lensing surveys cover only small areas of sky because massive lensing clusters are rare. Lensed high redshift galaxies provide detailed case studies but may not represent typical galaxies at those epochs. Combining lensed and unlensed samples provides complementary information. Lensed galaxies offer detailed resolved observations of a few objects, while wide field surveys like JADES detect larger numbers of unlensed galaxies to characterize the overall population's properties and abundances. Comparing observations. Understanding early galaxies requires observations across the electromagnetic spectrum, as different wavelengths trace different physical components and processes. Webb observes in infrared wavelengths from 0.6 to 28 micrometers, capturing rest frame ultraviolet and optical light from high redshift galaxies shifted into the infrared by cosmological redshift. This light traces stellar populations and ionized gas heated by stars. Ultraviolet light from hot young stars provides information about star formation rates, while optical emission lines reveal gas properties including metallicity, ionization state, and kinematics. However, other components require different wavelengths. Cold molecular gas, the raw material for star formation, emits most strongly at millimeter and radio wavelengths through rotational transitions of molecules like carbon monoxide. Observing molecular gas in high redshift galaxies requires facilities like the Large Millimeter Array, which has detected molecular emission from galaxies at redshifts up to 7, revealing substantial gas reservoirs fueling star formation. Dust in galaxies absorbs ultraviolet and optical light from stars and re-emits the absorbed energy at far infrared wavelengths around 100 to 300 micrometers. This dust emission traces obscured star formation where stellar ultraviolet light is absorbed before escaping the galaxy, causing the galaxy to appear faint in ultraviolet but bright in far infrared. Webb observes only out to 28 micrometers, which at redshift 14 corresponds to rest frame wavelengths around 2 micrometers. Still in the near infrared and not reaching the far infrared dust emission peak. Observing dust emission from galaxies at redshift 14 requires submillimeter and millimeter wavelengths where the dust emission peak shifts due to cosmological redshift. ALMA has the sensitivity to detect such emission, and several high redshift galaxies discovered by Webb are being followed up with ALMA observations to measure dust masses and obscured star formation R8s. These observations reveal whether early galaxies contain significant dust, which would imply that dust grains formed quickly from metals produced by the first supernovae, or whether dust was rare, indicating that ultraviolet observations capture most of the star formation. X-ray observations trace hot gas heated to millions of degrees and black hole accretion. Supermassive black holes accreting gas emit powerfully in X-rays, making quasars bright X-ray sources. Observations with X-ray telescopes like Chandra have detected some high redshift quasars, revealing black holes accreting at high rates. However, less active black holes or those obscured by gas and dust may not appear bright in X-rays, making X-ray surveys incomplete for finding all black holes in early galaxies. Future X-ray missions with greater sensitivity will improve X-ray observations of high redshift objects, complementing Webb's infrared data. Radio observations detect synchrotron emission from relativistic electron spiraling in magnetic fields, tracing supernovae remnants, active galactic nuclei jets, and cosmic ray populations. Radio emission from high redshift galaxies is faint and requires Sensitive facilities like the Square Kilometre Array currently under construction to detect. Routinely, comparing multi-wavelength observations enables comprehensive modeling of galaxy physical conditions for JDSGSC 140. Webb provides ultraviolet and optical rest frame spectroscopy and photometry. Future ALMA observations could measure molecular gas mass and dust emission if an active galactic nucleus is present. X-ray observations might detect accretion signatures. Radio observations could detect synchrotron emission if supernovae or an active nucleus produce relativistic electrons. Combining these datasets constrains the galaxy's total mass budget, including stars, gas, dust, and black holes, the energy budget including star formation, black hole accretion, and feedback, and the chemical budget tracing metal production and distribution. Such comprehensive studies have been performed for galaxies at redshifts 2 to 6 where multiple facilities have obtained extensive data, revealing diverse galaxy populations including dusty star-forming galaxies, quiescent galaxies where star formation ceased, and active galactic nuclei. Extending similar studies to redshift 14 and beyond tests whether early galaxies resemble lower redshift systems or represent a distinct population formed under different physical conditions. In the younger universe,